thanks for Anna's introduction. So first of all, I would like to thank Anna and Christian for the wonderful 5 days. I think, yeah, this is the 5th day. Like explaining a lot of good ideas to us and answering our questions. And most important of all, like stay up late with us until 12 o'clock. Right, okay, let me just say, what's the thing that we proved? Sorry, this is kind of messy. Okay, so in Scholz's torsion paper, he proved the, this kind of cohomology vanishing result. So we consider the gamma infinity level modular curve, and then we consider the compactly supported completed cohomology valued in Fp. And then the result he proved was that this guy would vanish above middle degree. In particular, we just work on modular curve, so this guy would only have cohomology at 0 degree and the 1st degree. So the goal of, what we have done for our project is that we we prove another version of this cohomology vanishing result, namely replacing the gamma level by the gamma 1 level. Okay, so why do we care about this? The reason is that once we know this kind of cohomology vanishing result, we have a better chance to eliminate the nilpotent ideal, which appeared in the Galois representation associated to a torsion class, which was constructed by Scholz in the torsion paper. So, to be a little bit more precise, the Galois representation is from we have the Galois representation, absolute Galois group of Q, and then mapping to GL2 of the Hecke algebra modeled by some nilpotent ideal. But we know that classically we don't really need this nilpotent ideal. So we would like to eliminate that nilpotent ideal. So the source of this nilpotent ideal comes from the excision sequence involving the boundary of the modular curve and then the open part. So it makes sense to compute this compactly supported cohomology and then know more about this cohomology. Okay, so now let me go back to how we would like to prove this cohomology vanishing.
Could you hold the mic a bit, please?
Oh, sorry. I thought my voice is usually very small. Sorry.
Very low,
okay.
not small.
Alright, so the first step is to reduce our goal to the following. Like, we want to prove that on this side, the cohomology of the compactified gamma 1p infinity modular curve with value inside this sheaf I plus over p would be almost 0. So why we can reduce to this statement is from another result by Scholz of primitive comparison. So if we tensor our original completed cohomology to OC mod p, then we have this almost isomorphism to this coherent cohomology. And then it would suffice to prove that this coherent cohomology would then almost be 0 for degree greater than, for degree above, for above middle degree. Okay, and then so to explain a little bit what this sheaf is, this I is the ideal sheaf of the boundary of the modular curve, and then the I plus is the part of this ideal sheaf which, the functions takes value, the function is bounded by 1, so the I plus that usually appear in the Boole pair. Okay. Before going on, let me just recall a little bit, like, why is it difficult to directly like follow the same argument and then prove the result for gamma 1. So the essential ingredient in proving the vanishing result for gamma 1 is that we know this gamma level modular curve is actually perfectoid. And then we have the Hage-Tate, to prove that it's perfectoid, we use the fact that we have a perfectoid anti-canonical locus lying inside this gamma level modular curve. And then we can use the Hage-Tate period map, and then the here is GO2 QP action on the modular curve to translate this perfectoid anti-canonical locus to the whole modular curve. So our gamma 1 level modular curve would lie below the gamma level modular curve, which would not be necessarily perfectoid. So that's where the difficulty comes from. So now I'm going to tell you the strategy of our proof. Oh, sorry, I forgot to put the. Okay, the following is our strategy. So because we know that the gamma 1 level modular curve might not be perfectoid, so we want to separate this modular curve into two parts. The first part would be the canonical locus, namely like it will lie above the canonical locus of gamma 0, which take out the canonical subgroup for the order P subgroup in the gamma 0 level. And then the second part is simply the complement of this canonical locus. So we would call it the non-canonical locus. So just warn you that non-canonical does not mean anti-canonical. Okay. Right. And then the third step is to use Merivia-Torres sequence to combine the vanishing result on these two separate locus. So you would ask, okay, the canonical locus should be a closed subset, while the non-canonical locus is open. How could I use Merivia-Torres? So in reality, we will replace 1 by an open neighborhood, which we will call UC. And then we will replace the non-canonical locus by an open subset called U and C. Okay. Now, just to give you a little bit more idea like what this canonical locus and non-canonical locus look like, I'm going to show you a picture which was predicted by Anna from yesterday's lecture. He said that we have to draw some picture to show you. All right, so this is the picture. We have the gamma level modular curve here, and then the Hage-Tate period map to P1, the Ali P1. And then, so for the canonical locus, under the Hage-Tate period map, it will map to this infinity point on this P1. Because remember that our Hage-Tate period map is simply like if we have an ordinary elliptic curve with gamma level structure, then we use the Hage-Tate filtration to have the one element to pick out the canonical line inside the Piaget-Tate module tensor with C. So yeah, the canonical locus would just by definition be mapped to just one point, the infinity point. And then so the non-canonical locus would of course map to P1 minus this infinity point. And then just for your reference or for curiosity, the anti-canonical locus would actually map to these green dots on the lower hemisphere. So because the anti-canonical locus actually lies in the ordinary locus, so we know that it should map to QP rational points on this P1. And in particular, you will only see them lying on the lower hemisphere. And remark, I'm going to tell you like why they don't like where are these QP rational points on the upper hemisphere. So let me show you another picture. So recall that if we have a p to the m, order p to the m's subgroup dm inside the p to the m torsion of an elliptic curve, then we say this subgroup is anti-canonical when we take the p part of this subgroup, then it will intersect with the canonical subgroup trivially. So pictorially, if we look at the e to the p, the p torsion of the elliptic curve, for ordinary elliptic curve, we would have the mu p part and the z over p part. And then, so for it to be anti-canonical, we have to choose the right branch already at the level p level. So we have level p. So we have to go to left to be in the anti-canonical locus. And once you enter this correct way, then there is no other chance for you to be lost. You can just go straight toward anywhere you want, and then that would be the anti-canonical locus. However, for canonical locus, you could make the correct choice at the p level, so you choose mu p. But in order to be in canonical locus, you have to always be very careful to always make the correct choice to choose the mu p part and then to have the canonical locus. If you ever made the wrong choice between, then you will end up in something between anti-canonical and canonical. And these would be the points that you didn't see. Those would be the points that are the QP rational points on the upper hemisphere.
When you've written can and NC, do you mean should that be gamma 1 or should that be gamma?
Can you say your question again?
When you have star can and star NC, that should be gamma 1, just to be, or should
You mean the picture? So the canonical locus and the non-canonical locus, I can define it for gamma 0, gamma 1, and gamma because canonical, this concept already appears in gamma 0. So that just means when I write gamma canonical, which I do here, that would just mean the pullback of the canonical locus on gamma 1. Okay. All right. Let me take back my previous page. So I ended my side remarks. So now I want to begin the first step. And I just realized that I forgot to tell you. I'm going to talk about the first step, and then Luan will talk about the second part, and then we'll talk about the Merivale-Torres part. Yeah, I'm sorry. I forgot about you guys. Right, so now let's begin to talk about the first part. So we have to choose smartly open neighborhood of the canonical locus. And what we'll do is to choose an open set on this P1 defined by the longitude line. And then pull that thing, I will call it straight UC. And then the thing I pull back to gamma level modular curve, I will call it UC tilde. And then the thing that I take the image of this UC tilde, I will call it UC. And after smart choice, we want to use this UC for our Merivale-Torres sequence. So let me make it more precise. Okay, so I told you that we will choose this UC, which is some part of the upper hemisphere in the P1, and we will just choose it a little bit smaller than the upper hemisphere. And then, so after we pull it back to UC tilde, this guy would be aphenoid perfectoid. This is very important. And why this is true is because we actually know that on the P1, if we pull back the part that's defined by the equator, namely if you pull back the upper hemisphere, then that would be affinoid perfectoid in the gamma level modular curve. And then we choose this UC be a open subset of that, defined by, we choose this UC to be a rational subset. So when we pull it back, it will still be a rational subset in the affinoid perfectoid. So in particular, this UC tilde will still be affinoid perfectoid. Right. So why we choose this UC be a little bit smaller than the upper hemisphere? The reason is because we want to be able to have a good UC after we push forward this UC tilde. So this UC, sorry, I think there are two UC. This straight UC is chosen such that when I pull it back to UC tilde, then that would be stable under the unipotent action by this matrix 1ZP01. And this is the matrix that we have to quotient in order to go from gamma level to gamma 1 level. So because this straight UC we choose it such that the valuation of the coordinate is negative. So when we translate by ZP, the valuation wouldn't change. Okay, so now we have good choices of straight UC, UC tilde, and UC. Now, we know that this cover from the gamma level modular curve to the gamma 1 level modular curve is a ZP covering in some suitable sense. So to compute the cohomology for the UC, we can use the Cardon-Larray spectral sequence, which tells us that if we want to compute the cohomology on UC, we can first take the cohomology for UC tilde and then take the continuous cohomology of the ZP action.